So this brings me to the biggest challenges in this presentation when I tried to set it up. So I gave myself this title, and it's a critical and problematic issue talking about sample preparation and sample preservation in the end. If we talk about unstable colloidal systems, which we always have to focus on, if we talk about environmental nanometrology. So I introduced already myself, so I'm a public servant most of all, and I explained to you why I'm doing this cost action and why I'm the chair of this cost action. I'm really happy about that. And this is where I started. So in natural wetlands, I'm basically taught in environmental sciences and come from the soil sciences side and sediments, and got my PhD in environmental analytical chemistry. And this is what we're interested in. If we talk about natural wetlands maybe, and the other part, and I already mentioned that, a workshop in Pula, where these slides from Florent are from. Maybe in the beginning the more interesting part, because they receive much more of the load, are the constructive wetlands, and I try to give you an idea. If you start with nanomaterials and wetlands, independent from if you want to ask a question on this or that, or mesocosm experiments like I run in my laboratory at the moment. So the question is, in the end, can we transfer somehow the result from the lab to the field, or do we need now full-scale experiments for the future? So when we started with this think tank in Penn, we asked several questions. So what is the wetland scientists hindering to perform nano studies? What is nanoscientists hindering to perform wetland studies? And what are the major challenges? And I think still, and I agree with Ralph, that this is the major obstacles are the environmental nanometrology at the moment. So what makes them, the scientists, feel uncomfortable in the respective other field in the end? This is the question we've got to address. Maybe, and how can we support in the future better teamworking between the small nanoscientists and the big wetlands? Huh? This is what this workshop is in the end about, and I hope that we can provide a little advice in the end and give you an idea where are the major challenges and what is already doing well in our working field. So I've already addressed all of this, and I think wetland scientists can explain something like this. This is was caused, we spiked something like 10 ppb titanium dioxide to a soil column, and what we've seen is preferential flow to the wall in case, and it was caused an agglomeration surely, and it was simply caused by earthworm activity in this case. Yeah. This is wetland. But much more interesting for the wetland people, I think, which buzzwords do we need, and this is environmental nanometrology. And what are the key questions from my understanding? It's always my biased point of view, maybe, and this is how to fix and preserve the colloidal status of an unstable suspension. This is really a critical and difficult issue, and there's no best practice. In the end, please just let me, I always show this slide, mention speciation, and it's based on the definition by Templeton. It's a UPAC definition, and it's all about speciation and fractionation in the end. And so speciation is a term that defines an element as characterized by its isotopic composition. This is a very nice tool if we want to do spiking experiments for stable isotope labeled particles. It works fine with certain limitations. It's about the electronic or the oxidative state. Sure, iron is a very important measure in wetlands, so this is about oxidation and reduction. And the complex and molecular structure an analyte is in. And this leads over to fractionation, because we talk here about a specific form, and here we talk about a process of classification in the end. And so it classifies an analyte or a group of analytes according to the physical, and here a very important parameter comes in, or two parameters. This is size and solubility as examples, and the chemical composition, and this is bonding and reactivity, which is quite important in the end altogether for availability, toxicity, and mobility, which we're interested in scientists in wetlands. So a very simple non-nano example, and I can save some time by rushing through it because I mentioned it already in the discussion before, is sieving. So, and still after introducing this instrument more or less 20 years ago, so we've got here the sieving device, we've got here the laser diffraction, and here a new camera device. There are 5 different, or 6 at the moment on the market, and displays very easily how difficult it might be with this simple example where we have a sand-rich soil sample and a clay-rich soil sample, and compare these 2 devices, and it works fine for the sand, this comparison between sieving and laser diffraction, but it doesn't work so nice for the clay system. And this holds true, as I've already mentioned, also for the nano-analysis. There's no difference. If you've got 2 independent methods, you might receive different results. And we need, on this side here, algorithms, if we want to directly compare it, to change our distributions. So, another, why is that? It's very simple. Here, the quality of your analysis depends on the quality of your mesh size and your mesh. And here we've got additional parameters which are simply visible in this camera-based system. And in the end, we need something, if we want to compare them, to calculate, base our calculations on, to compare these results. So, my advice is, and I don't think that you can see it from behind, is don't try to mix a bunch of methods in your initial studies. Try, and I repeat this within this presentation again and again, try to find the limitations in at least 2 methods, define them, and work with at least 2 independent methods for the concentration and the size analysis. Okay, if you start, this is sufficient. So, what are the biggest challenges in the end, taking this together? Most scientists are used to work with dissolved species. What is this? I'm going to mention later again, critically. To think and include in experiments the particle size distribution, the concentration, and maybe also the speciation is tricky. Right? And it takes a lot from you to think in 3 dimensions in a single study in the end. What are potential artifacts from storing? They occur anyway, we know that. And from sample preparation, and we've got to address these artifacts, sorry for that, artifacts in all 3 points in the end. This is an additional factor which have to be addressed in the future. And due to these 2 points, good or best practice advice as well as certified reference materials are missing still. After, I think we talk about this issue now for more than 10 years. But they are still not on the market, for good reasons. Okay, what about the dissolved species? So, as a basic input quantity, you want to do a spike in your wetland experiment, you've got to know if there are dissolved species from your particles. And I think we all agree that 0.5 micrometers, 450 nanometers, doesn't help so much in the end. And this is based simply, and I asked this question at ResearchGate and received nice answers, especially by these 2 guys here, by Philippe and Sanya. And this is an operationally defined convention, and it's a relic from the 30s. It's based on the available minimum purity of cellulose acetate filters at this time. And it's included in many standards, and we can't get rid of it anymore. What does it mean for you if you want to start your studies is take your own decision. What's the definition for a dissolved species? In the end, it's up to you. It has to be somehow reasonable and explained in your publication, but you're quite free to address 1000 nanometers or 100. You can address it by filtration, and this is a critical point. You've got to name your separation technique in the end and make it visible and explain it. So we tried to give, in 2014, Annalena Fabricius published that, something like a good practice advice, at least for the total content analysis by ICP-MS of nanosuspensions, and how to address the dissolved species in the end. So this is a simple sheet given you an overview which separation techniques are available for dissolved species in the end. And you have got here as basic principle the in situ or ex situ preparation for the ionic species or dissolved species. Passive sampling like DGT or PPERS works fine, or suction beige, which also works fine for nanoparticles from my experience. We've got different hollow fibers for in situ work with different cutoffs from 10 micrometers down to 7 kilodaltons, and so it's a very simple approach which works for initial studies, I think, quite good. If we separate our samples from the wetland, we've got two different measures. This is the bulk phase and the liquid phase, and also by the traditional methods we can address that. We've got squeezing, centrifugation already addressed by Ralph. We've got sedimentation, filtration, which is, from my understanding, mostly used. We've got freeze drying and so on. So what we need in the end for our design is to address the sample preparation, the sample preservation, which are most critical points. And then at least we need two measurements or techniques to address the size aspect and the concentration. And as also Ralph mentioned already, a pragmatic thing would be if there's no total content signal, why do fractionations? Very simple. Is there overburdening diversity? And I agree with Ralph, there's not. At least there's 3 to 10 methods at the moment which are frequently used in environmental analytic chemistry on engineered nanoparticles. And so please keep in mind, and I support Ralph's statement on that, if you use certain measurements, and these devices, for the scattering devices, are very helpful to characterize your emission spike. And we use the NTA as one example to characterize also the colloidal status of an unknown sample, which is really nice because you can have a look on your sample. But if you apply these methods to complex matrices, it might be difficult, and maybe you see an invisible bichromosome. It leads often to misunderstanding. So, the needs in complex matrices are quite clear. We have the particle sizes, we have the concentration, we have microscopic measurements, which are nice. From my understanding, most important for the concentration are ICP-MS and AAS systems at the moment. And we've got separation systems, as already also mentioned by Ralph. And I would like to add here the cloud point extraction, which is, from my understanding, the only option at the moment to concentrate our analytes in a complex matrix. So, what about needs? So, there are regulatory needs or monitoring needs that I'm interested in. And if we ask, as per definition mentioned by Alvar, for a number-based particle size distribution to classify a material, we have contract laboratories on the other side, and they need simple advice and simple methods to do regularly monitoring work for us. And so this interferes somehow from my understanding, and we need a solution for that. Independent, if there are particles at the moment in the surface water or not, we have to address this. And we've got scientific needs, and so my advice would be use one of the common definitions that serve your scientific needs and stick to it all over your study. Don't change it in between. I've seen that several times, it's not so good. And the analysis will most likely be quite complex if you want to go down to mechanisms and really have a deeper look on what is going on. So, what is a sophisticated analysis or method, in my word, and what is a simple method that serves regulatory needs? So this is sophisticated from my understanding. For coupled to sector field ICP-MS is not something you can do in a contract laboratory every day at the moment. This might change over time. And on the other hand, we've got something like cloud point extraction coupled or combined with AAS analysis, which is a very simple, cheap method that you can apply to your complex matrix from my understanding. And in between, we've got other options like the single particle ICP-MS, which was already addressed and explained by Ralph. And we've got combinations maybe in the future of these different methods. Common thing is, know the pro and cons of your method that you use. Which limitations are given in the literature, which have you seen in your own work, and please communicate these limitations in your publications. So, maybe an experiment, and this is about to hand over to Greg, might be, we've got our wetlands, we've got our plants in our wetlands, we want to do a nanospike or something like that. We've got a certain enrichment in a certain compartment, and we wanted to cross-check this with, where are our analytes going in these, and how is the interaction in the different cycles in this wetland. And in the end, maybe we want to do also release studies or speciation, or we want to check whether there's a reversible binding of our analytes in the system. This is quite challenging. And in the end, maybe you come up with a scheme like this. This is just an example. I could have taken another one, but I stick to this. I think we can get rid of this. In the end, you've got some kind of method for concentration, for particle size. You need to address separation and size fractionation, and this defines your pretreatment. So, for each matrix, you need to address the artifacts which might be formed within each step. And this defines your overall uncertainty in your experiments. So what about environmental versus analytical realism? And I disagree at a certain point with Ralph, and it's quite pragmatic to start here in the end, because it doesn't help you so much if you do a wrong spike in your system and you are totally under your limits of detection. This is a waste of money. So what we need is a certain realism between what we can expect in the environment in the end and what our analyses need. And we do wrong if we do very high spikes here, we know that. But in the end, it doesn't help so much if we've got no signal in our analysis. This is really tricky, this part here. So, to put things together, from my understanding, sample preservation depends on your questions, and in speciation and fractionation studies, not only for nanoparticles, there's no real best practice, there's only methods that are not as bad as the other. Maybe it's good to avoid crystals during freezing, so shock or flash frosting for some analysis might help. Freeze-dry might be a good idea if you want to address the bulk phase. Measure your sample as soon as possible. This is banal, but it holds true for all parts in environmental analytical chemistry. Define clearly your scientific needs and choose at least 2 methods that give you benefit for your scientific needs. Be always aware of the limitations of these methods, and please address the limitations also in your publication so others can better follow your interpretation. So, thanks for your attention, and I hope we can bring you a little bit forward with this.